So as Themis has explained, every time I come to visit CSCS, this is my third visit now, so it's a pleasure to come back and see new users and help people to use these systems. But everything just gets bigger. When I came here before, the first time, it was the old site away over the hills. There were donkeys outside, and there were just 2 cabinets of Cray XK6 with Fermi GPUs. When I came back, I think it was February time this year, there were 3 cabinets of XK7 with the Kepler GPUs. And suddenly you come back and there's 28 cabinets of GPUs. So if I do get the opportunity to come again, I hate to think how many cabinets I may find if this increase continues. It is, I mean, Cray is very proud of this machine. It's certainly the very biggest hybrid machine that we have installed. It's on the Green 500 list, as was pointed out, it's orders of magnitude larger in size than the machines above it. And it's the biggest supercomputer in Europe. We're very pleased with that. But using a hybrid multi-core system like this is not easy. It's not as straightforward as before. I mean, you can say whatever you like. There's all sorts of tools to make it easier, but it is more difficult. It does require some user effort to get your codes up and running on these systems. So what I'm going to talk about today is OpenACC, and this is an endeavor, a sort of cross-vendor recognition across the industry that these things are difficult to arrange. It's difficult to get your codes across to there. So we must provide a programming environment that makes it easier. I mean, if you want to say what is a programming environment, it's something that kind of it bridges the gap between the peak performance of this machine and what you can achieve with your code as a real user doing a real calculation. So OpenACC, or OpenACC as I will sometimes call it, is an effort to make this, to take a code that you have that's running on the CPU and allow you to make incremental changes to this code so that it can be run on a hybrid multi-core system, an accelerator, which at this stage, I mean, we're talking specifically about the Nvidia GPUs that are sitting in this machine, but it's more general than that, and it can be applied to other architectures. And you do this by recompilation and some tuning as opposed to a complete rewrite. So OpenACC was launched at Supercomputing 2011, so that's 2 years ago. It got an award last year as a technology to watch. This year it got 3 awards from HPC Wire, 1 Reader's Choice Award and 2 Editor's Choice Awards. So these were displayed on the booth at the Supercomputing conference, and Cray was there giving a tutorial very similar to this. So they have these tutorials on the Sunday and the Monday, and we had an all-day tutorial on the Sunday to teach people about OpenACC. And of course, you come back fired with enthusiasm. I must change this, I must update this, this didn't work very well. So I've made a lot of changes, so I apologize if there's places in the slides where something's slightly out of date. I will correct that before I distribute the PDFs, which I think you can put them up on the website, can you? The PDFs for the talks. So please bear with me if there are any mistakes. So one of the things that I decided that I would change was to split the material up a little bit more through the day to make it into, so rather than having 1 or 2 or maybe 3 lectures on OpenACC, I've split it up into six sort of parts of the programming model as we go through the day, and they kind of build in complexity. So we also have some, well, hopefully a live demo. This is a bit of an experiment. If not, we will, I have a worked example where I go through taking a simple code and putting in OpenACC and running it and showing how the performance changes as you go through the porting process. It's a very simple code. I mean, it has to be if you're doing it in a demo there. And you'll notice that it's very early on in the day. It's just after the coffee break. And the reason for that is that to port a code, you don't need to know much of OpenACC. OpenACC, I mean, they have what they call a quick reference guide, which doesn't seem so very quick these days. But there's a lot in there. And it gives you a lot of flexibility and a lot of things to do. But a lot of this is more advanced. To actually get a code up and running, you don't need to know very much. So but what I will talk about in this first lecture will be enough to port this simple code. You won't get the optimal performance, you can tune it, but the point is you can port this code to run entirely on the GPU just using that knowledge. And you'll get a chance to do this as well before lunch. But then in the other lectures, I'm going to talk about the more complicated things and the ways that you can get performance and the ways that you can deal with real codes that contain sort of real computational tasks as opposed to the simple examples. So I don't want this to be something where you just go away and you've got hello world and that seemed to run fine, but then you go and you take a real code and you say, well, where do I start? You know, what do I do? That's not what this course is about. This course is, I'm assuming that most of you here work with real applications, industrial, scientific, engineering, whatever, but they're doing real tasks and you're going to want to port the entire application and you're not just interested in a very simple example. So how many of you here have used GPUs before? Right, I'm not really going to assume you have. If you've used CUDA, some of the language will be familiar. If you've not used CUDA, you don't need to know it in order to do this. Similarly, how many of you have done any OpenMP programming? So a similar proportion, about a half. Again, OpenMP is a similar programming model that you use on the CPU. If you've done OpenMP, there are some similarities with OpenACC. And there are places where I'll sort of say, this is the same as OpenMP, or this is different to OpenMP. But you don't, again, I'm not relying on you knowing OpenMP in order to do this. And similarly, all of the practicals that I'm going to talk about, except the only thing is when I say porting a parallel code here, this is some extra things if you have a code that's got MPI in it. This may be relevant to you, it may not, but that's the only place where I'm really going to be talking about a message passing parallel code. So before we start the main course, so I kind of talked mostly about this. My background before I joined Cray was I worked in lattice QCD, calculations, theoretical physics. So I always think that I come to computers with more of a user view than somebody who's kind of come from compiler science, you know, a computer science compiler development type of point of view. So in some cases, I'm probably going to skip over details, either because I don't think they're that relevant, or more likely because I don't understand them. So please ask if things seem a little bit high level. But the other reason for that is that unless you are trying to get the last few % of performance out, you don't really want to care about the architecture. I'm guessing most of you have run a code on a CPU. How many of you do any assembly language programming? There's always one. But most of you don't. But you could get better performance on the CPU if you rewrote your application in assembly language. But you don't, because you want a portable code. And that's the same approach I'm taking here, is that, yes, if you really get down and you write your kernels in PTX, you'll probably squeeze a bit more performance out of the GPU, but it won't be very portable, and in some ways it won't be very productive in that you'll spend a lot of time to get that extra performance. If you want to do that at the end, well, that's the sort of the last stage of optimization, but that's not where you want to start from. So again, that's the approach I want to take with this. But it does help to have a little bit of an overview of the architecture that you're using, because some of the language that I use kind of relies on what's happening underneath slightly. And also, you cannot ignore the architecture, because a GPU is a very slow serial machine. It's a very good machine when you use it properly, but you have to understand a little bit about the architecture to get the good performance. So the Cray XC30, and also, I mean, the XK7, like Turdy, are very similar. They have nodes linked together with an interconnect. For the XC30, it's the Cray Aries interconnect, which is a sort of multi-level all-to-all network. It uses 3 levels of all-to-all, 2 with copper wiring, and then it also uses optical cables between groups of cabinets. So it gives you very good global bandwidth. And this amount, actually the amount of global bandwidth is tunable. You can choose how many optical cables you put into your system. And one of the amazing things about the machine at CSCS is that it's one of the first systems, well, that we could talk about that has the full complement of optical cables. So this machine has the best bandwidth of any Cray XC30 that you would ever be able to use in the world. So another great feature of it. On the node, you have one CPU, which on PISDount is an Intel Sandy Bridge, 8 physical cores, and it's got one Nvidia GPU, a Kepler K20X. Turdy has an AMD Interlagos CPU, but the same GPU. And it has the previous generation of interconnect, the Cray Gemini. For this course, that's not going to affect you because we're not really using the interconnect. And as we've talked before, power is a big thing. Why are we interested in accelerators other than we're using them now? If we're going towards exascale machines are going to have a lot more computational power, but without using physical electrical power to run them. The DOE says it'll fund an exaflop machine, but it only wants it to be 20 megawatts. Well, the Jaguar system at Oak Ridge, to get a petaflop, was using 6 megawatts. Things have improved since then, but not to the point where we can get 1,000 times more performance with 3 times the power budget. So accelerators are going to be very important for that. And if you read the exascale roadmaps, a likely way to reach this is that whilst you have more nodes in your system, the nodes have a lot more, they're a lot fatter, they have a lot more computation per node. And this is probably going to come from accelerators. These aren't going to be all Intel Sandy Bridge, Ivy Bridge CPUs because they take too much power. They're going to be much more cut down. They're going to look much more like a GPU core. So the work that's done now in understanding how to use GPU accelerators is going to carry forward for the foreseeable future. We're never going to be going back to a situation where you simply just use ordinary CPUs and you will be able to have an exaflop machine. So if you look inside the machine at the node, you pull out one of these blades that has 4 nodes on it. It's got 2 daughter cards sitting on it. And on those daughter cards, each has 2 nodes. And that consists of a CPU, which has, well, kind of 200 gigaflops of performance, 32 gigabytes of RAM, maybe 50 gigabytes a second of bandwidth between them for memory bandwidth. There's also a GPU. It's hidden under the heatsink here. This gives you about, well, over a teraflop of performance, slightly less memory, 6 gigabytes, big memory bandwidth with this GDDR between them. But the bottleneck is the fact that these are 2 separate things, and between them there's a PCI bus. And this PCI bus is relatively slow. It's much slower than the memory bandwidth there. And this is everything about GPU programming. You've got 2 memory spaces, 2 physical memory spaces. I know that with different new programming models in CUDA and the like, you're having unified memories models and so on. But they are still physically distinct, and things have to move from one to the other. Data has to move from one to the other. And when it does, it moves along a slow link. Everything about GPU programming, everything about OpenACC is about data locality. It's putting the data where you want it, processing it there, keeping it there for as long as possible, and only moving the data that you need to move, and, more advanced, when you do need to move it, try and do something else while you're waiting for it. If you look at the sort of ratio of the memory bandwidth here, it's about a factor of 5. If you look at the ratio of the floating point performance here, well, it's maybe a factor of 6, 7, 8. What this means is that if you get a code and it runs really well on the GPU and gets peak performance, you're not going to get 1,000 times faster than your CPU. This is a myth. You will expect to get something like, for a memory bandwidth bound code, a factor of 5 in performance. You can't do better than that. So, and the other problem you have, of course, is that it is harder to get peak performance out of a GPU compared to a CPU. So you should have a realistic expectation about what you're going to achieve by doing a GPU port. It can speed things up. You can get factors of 3, 4, possibly 5, depending on exactly what the code does. And that does justify using the GPU as opposed to the CPU, or even better to use both. But you shouldn't, the hype of how many tens or hundreds of times faster doesn't hold. Within the GPU, what does it look like? Well, you've got a lot of floating point cores, but they're split up into groups. And each group is called a streaming multiprocessor. There's 14 of them on the Kepler. And within that group, it's got lots of cores, but they're all doing the same thing at the same time. So it's if you kind of go back, it's a vector processor in the sense that it's processing vector instructions. It's saying, everybody do this now. Everybody do this computation. Everybody load from memory now. Everything's done with vector instructions. And that's very important, because if you have a very serial code, yes, it will use vector instructions, but it'll only use one lane of the vector instruction, and you'll waste performance. So everything is about trying to get your code to vectorize at the lowest level. You then have, when your code is sent out to the GPU, it's split up into blocks of operations. And different blocks of operations will go to different ones of these streaming multiprocessors, these, if you like, vector processors, which operate essentially independently. There's no synchronization between them. So in GPUs, it's very difficult to say everybody reach this point in the kernel. You can say everybody reached this point within one of these blocks, but the different blocks are doing different things at different times. And that's very important when we come to understanding this. So each core has its own registers for holding small amounts of data, part of the calculation. Within a block, they share some what's called shared memory, which is a little bit of, if you like, it's like a cache that can be used. And then there's a very large global memory that they can all go to, which is where you store your main data. But going to global memory is relatively slow, and you need to make sure that you access it in an efficient manner. GPUs, whether you're using CUDA, OpenACC, or whatever, it's host directed. The CPU is in charge. The CPU tells the GPU to do something and then waits for it to do it. The GPU doesn't really do things on its own. This has changed slightly, I know, with the sort of some of the more modern developments, but generally everything is controlled by the CPU. The CPU manages memory on the GPU, it launches the kernels, it does the data transfers and does the synchronization. You have these separate memory spaces, and they are separate. Different things can happen in them. You have to explicitly be in control of all the synchronization of the memory. Now by this, if you were writing CUDA, it is explicitly you that's doing that. If you're doing OpenACC, it's partly you that's controlling synchronization, and partly the compiler is helping you. So when you launch a computational task, these are generally called kernels, and these are a large parallel task. There's a lot of different operations to be done in parallel, typically all the iterations of a loop. And so each of this parallel work is divided between a large number of threads. And if you like, these threads are separate computational tasks. Now, as I said before, these are divided up. You have lots of these threads. They're divided up into groups, which are known as thread blocks. And one thread block gets assigned to one of these vector processors. But different thread blocks will end up on different ones. So threads within a thread block share some memory. They have this shared cache. You can do some synchronization. But for the threads that have gone to different ones of these vector processors, you've got no real control about what's going on. When you do CUDA programming, you have this concept of threads and thread blocks. What it doesn't have in the CUDA program model is this concept of warps. But if you don't know about warps, everything performs really badly. What warps are, essentially, is what I was saying before. Everything is done in vectors. Everything is done in blocks, where 32 cores do the same thing at the same time. So there's one vector instruction with 32 elements, and these are executed by the cores. So when you have your threads within the thread block, if your code is not vectorizing in the sense of the CPU, if it's not generating efficiently vector instructions, you'll be wasting some of this computational power. And similarly, when memory is needed, it's loaded in blocks. It's loaded in blocks of 32. So what you want is to make sure you do the minimum number of loads. Memory bandwidth is high on the GPU, but the flops is also really high. So code will wait for memory to load if you're not careful. There's all sorts of tricks in the GPU hardware to try to hide this waiting, this latency. But you need to load data in an efficient manner. And what that means is that if you've got 32 threads that are all doing the same thing at the same time, when they come to require data, you want to make sure that you give it to them as quickly as possible. Give it to them in one vector load. So in one vector load, you give them 32 pieces of information, one for each of them, so they've all got their information in one vector instruction. And this is called coalescing in CUDA. And what that needs to do is you need to make sure that you access memory in the correct order. If you stride through memory, you'll need many more vector loads, and your code will go much slower. So trying to get this vectorization, we'll see all sorts of examples of this as we go through the day. So really, your compiler is taking your code and writing it in vector instructions, like AVX for the CPU. That's what an OpenACC compiler is doing for you. It's what a CUDA compiler is doing for you. But you need to make sure that it's doing this in an efficient manner. Now, one of the great things about the Cray compiler, of course I always say this, but one of the great things about the Cray compiler is it's very old, or at least it has a great history to it. The Cray compiler has evolved from the days where Cray, the early Cray machines were vector machines, and Cray made really good vector machines. So we knew how to write compilers that could generate vectorized code in an efficient manner. And that vectorization part of the optimizer never went away. It just, for a long time on the CPU, for SSE, it really wasn't exercising its full capabilities. It's been very useful when we've come to OpenACC, and now on the CPU with AVX and extended AVX and so on, it's also being very useful. But all this know-how to do with vectorization in the Cray compiler is there. So what does all of this mean? Your code needs to have a lot of parallel tasks to keep the GPU busy. That probably means it should be loop-based, and the loops should have large trip counts. If it's not, your code probably will be, should we say, difficult to port to a GPU efficiently, if it's not a sort of loop-based code. If it's got some task-based parallelism, that could be all right, except you probably haven't got enough tasks. You don't want a few thousand tasks, you want tens of thousands or millions of parallel tasks to keep the GPU busy. And so OpenACC is particularly targeted at parallelizing loop-based codes. Your inner loop must vectorize. So if statements inside your loop nest, they're not disastrous, but you shouldn't have too many of them. So the same is true for the CPU. If you can move your if statements out of the inner loop, that will improve performance. And you should access memory in the correct order. So basically that means that your inner loop, the vectorized loop, should be the fastest moving index of your array. And again, we'll see examples of this as we go through. So I've kind of said this. Will my code work well? You should probably have loop nests that process arrays. The loop nest should have defined trip counts. A while loop with a sort of a test and then an exit statement is not a great thing to run on a GPU. The data structures, well, let's not say should be simple arrays. Derived types in Fortran are all right. We've done a lot of work to support derived types. Pointer arrays, linked lists are going to be difficult because the memory layout is difficult. There are ways to do all of this, certainly with OpenACC version 2 that came out this summer. There's a lot more flexibility for dealing with this, but it needs a lot more low-level control. You need to, as a user, to do that. The compiler can't do everything of that because it's very difficult with a linked list or a pointer array to know exactly what you're trying to do from the compiler's perspective. The loop nest should have a lot of iterations. It'll work with fewer, but the GPU won't be very efficient. The loops should span as much of the code as possible. You should maybe have some loops very high up the call chain. You're in a loop, you shouldn't have too many if statements. The code can be task-based, but each task should contain loop nests so that we've got this parallelism in there. And then we can also find ways to overlap the different tasks in the code. So not all codes fit this. You know, if you've got some sort of graph-based thing, it's more difficult to port. But if you've got a sort of, you know, a typical science or engineering application where you're processing arrays of data, these map very well with OpenACC onto the GPU. And as I say, you know, if the GPU is 10 times faster, you need to port a lot of your code to the GPU to really see the speed up. Otherwise, the serial code will just kill you. You know, if you port 10% of your code to the GPU and the GPU is infinitely fast, you've only removed 10% of the runtime from your code. If you're really going to see performance gains, you're going to have to port most of your computational work to the GPU. And Amdahl's law didn't factor in the fact that moving data between CPU and GPU is expensive. So that's an additional drain. So you really want to port as much of your application as you can. So there are ways to do this. There's CUDA, there's OpenCL, but these are, you have to rewrite in a specialist language. The tools for these are much better than they used to be, but they're still not as easy to write as Fortran or C or C++. And if you get a new accelerator that doesn't have CUDA on it, what do you do? Something like OpenACC, which is a higher level programming model, is more portable in that sense. And you know, if you've got a CUDA version and a Fortran or a C version of the code, you have to maintain both of those, sometimes to run on the CPU, sometimes to run on a GPU. If you do the work, of course, CUDA can perform very well. And you know, in some contexts, people have ported entire applications in CUDA and got really good performance because they've decided to do it and they've invested the effort to do it, and they realize, you know, that on a different accelerator you may not have CUDA. But if you do it, you can get great performance, and you can see here the speed up of, you know, a lattice Boltzmann code on GPU. This is even on the Fermi's GPUs compared to the CPU. But this was done at EPCC in Edinburgh with expert developers who worked on it full time. Not everybody has that degree of expertise and time to do that. So directives are a high-level alternative. The idea is you take your original source code, which is easy to maintain and port and extend, and you insert essentially comments that help the compiler to retarget that code at a GPU. So the compiler will handle a lot of the repetitive work, allocating memory on the GPU, writing the statements to move data to and from the GPU. And if you've used OpenMP, of course, it's quite a familiar way of programming. Now, it's a high-level approach. Now, of course, any high-level approach, you know, there could be a performance sacrifice. And if there's a performance sacrifice, is that a problem? Yes, if it's too big. You know, if it's more than, well, we say 20%, but really, if it's more than 10%, you know, your OpenACC compared to some CUDA that you happen to have doing that job, that's a performance bug as far as we're concerned with the Cray compiler. But at the 10% level, we say, well, you know, you don't do assembler for the CPU. Maybe a 10% performance sacrifice is acceptable in order to have one code base to maintain and extend. And this is an old slide now, but this was an example from Oak Ridge. Oak Ridge got their very big Cray XK7, and they spent a lot of time working on key applications to port them across. And running on the CPU, this is one of the big kernels in the S3D application, writing in CUDA Fortran. I mean, this is a logarithmic scale, so the difference from here to here is quite big. The difference from here to here isn't so big. But the point here was that actually the OpenACC matched the performance of the CUDA Fortran, but it wasn't CUDA. It was the original code. It was the same code as for the OpenMP, but with a different set of directives, and conditionally compile one or the other. Now, I mean, the question people always ask is, yes, but if I do this, what happens in 2 years' time? Do I have to throw it all away? You know, has OpenACC got a future? Well, there's lots of machines now to run it on. There's Cray XC30s, Cray XK7s, and it's multi-vendor. PGI and CAPS already target Intel Xeon Phi and AMD GPUs using OpenACC. And of course, you've still got the same code to run on the CPU, so you're only maintaining one code base. So there's plenty of places to run it now. What will happen in the future? Well, Cray, PGI, and CAPS are all committed to support OpenACC in the future, and GCC is now getting mods going into the code base for OpenACC support. If Cray turned around to CSCS and to Oak Ridge and said, you know what, OpenACC, yeah, it was a good idea, but now we've got this really great thing, and it's completely different. You should use this instead. You know, the big customers would not be happy. We're not going to do that because they're the big customers. They pay our bills. There's a huge customer pressure to continue to run OpenACC and to continue to develop it. The OpenACC committee, which started with 4 partners, is now up to 18. Version 2 was finalized this year. They're now working on the next version. There's a huge growing interest, not just from the sort of compiler and machine vendors, but also from partners doing applications and tools who are all committed to taking OpenACC forward. So OpenACC itself will continue, but what will something else come along that's better? Could the compiler do everything for you? Yes, please. We've been promised a compiler that would do everything for us for as many years as there have been computers, but they've never quite managed it, which is good for us because, you know, otherwise we're out of a job. The user is very important. We've never managed it before for the CPU, and data locality is a bigger challenge again. Compilers will help a lot, tools will help a lot, but they will not replace the developer input. OpenMP Accelerator directives, these came in with OpenMP 4.0. And these are essentially doing a similar task to OpenACC. It's a directive-based way of targeting the GPU. And in some ways it's attractive because OpenMP is a sort of defined standard, it's an established standard. If a compiler wants to say it's OpenMP compliant, it will have to support the OpenMP Accelerator directives. Doesn't mean it supports them efficiently. You know, the Intel compiler supports co-arrays, but it's not as efficient at doing co-arrays as other compilers. OpenMP4 is very new. There are no compilers yet that support it. The 8.3 Cray compiler, which is due kind of first half of next year, should have the Accelerator directives part of OpenMP4 supported. Not necessarily performance tuned, but supported. But that will be the first compiler, and you know, others have it on their roadmaps, but they're not there. So using OpenMP directives now is not a good idea. The other thing I would say is that OpenMP4 is the first part of OpenMP to look at accelerators, and there are, as I'll talk about later, there are various important bits of functionality that are in OpenACC that are not in OpenMP, which are very important for getting performance from, say, an Nvidia Kepler GPU. So if you were to say, I will use OpenMP accelerator directives, you will have to wait before you can use them, and there will be things that you will not be able to do in the program model as it is. That's not to say it won't come in a future version. You know, the first version of anything is the first version, and you build upon that. And OpenMP has taken care to write their programming model in a way which is sort of future-proofed. that it will, it will scale to future accelerators and a wide variety of different accelerators. The work you might do with OpenACC is not wasted. OpenACC, when in doing a port to a GPU, there's coding and there's thinking, and the thinking takes far more time than the coding. OpenACC speeds up the coding for you, but it doesn't speed up the thinking, because that's what you have to do. It just gives you more time to do it. The thinking that you do, the understanding your application, you're understanding the data locality, understanding the data flow, optimizing the data flow, all of that work will carry over. So it's not wasted. You'll just rewrite it in a different syntax of directives if you decide further down the road that you want to do OpenMP, accelerator directives. Cray is very active in this. Cray co-chairs the OpenMP Accelerator subcommittee, so we've been very interested in this from the start. And the work in OpenMP predates the work in OpenACC, in fact. So what I'm going to do is I'm going to lead you through using this, and it's going to be, the way I'm going to do it is to kind of do it bit by bit, incremental approach. Rather than sort of telling you everything, this is the programming model, I'm going to introduce bits of the programming model as we go along. Some bits I may not really mention at all, and that's probably just because I don't use it very much. I've not found it useful, or more likely because I don't understand it, but I'll gloss over that. So I'm assuming you know a little bit about a GPU, but you don't need to know too much about it. And as I say, if you know a little bit about OpenMP, that will help. So are there any questions on that so far? Stunned silence. Please ask questions as we go along. Don't leave them. Just put your hand up, shout out, or whatever. So in this talk, we're going to do a little bit about basic directives. So I've said a lot of this already. It's supposed to, it's a portable standard. The Cray version 2 came out in the summer. The Cray compiler, the 8.2 release in September, had full support for that. There's a little bit of performance tuning going on in revisions to the 8.2 compiler. GCC support started in late 2013. They had some demonstrations at supercomputing. It's not production ready, I think, is a fair way to say what they're doing, but they're doing the solid groundwork that's needed. I've talked a little bit about execution and memory models. My eyes tend to glaze over at these things. This is sort of computer science. But essentially, it's the idea that, same as in CUDA, your main program runs on the CPU. Your main program gives tasks to the GPU and manages the memory. And yeah, there's no automatic data synchronization going on between these memory spaces. And similarly, the host is responsible for all the synchronizations. But the compiler and runtime help a lot more in OpenACC than they do in, say, CUDA. So how does it work? The idea is you put comments in your code which give hints to a compiler. They're comments, so if the compiler doesn't support OpenACC, or if you tell it, I don't want to compile the OpenACC part of this, it will produce a code that runs on the CPU. So these are specially formatted comments. In C, they look like hash pragma, ACC, something, and then a structured block. In Fortran, you have ACC, star, a structured block, and you have an end directive just because you don't have the concept of curly brackets in Fortran. The lines can get quite long, and you can continue them. Now, in theory, that's all you should do. You should just put these comments in, and you have a code which either runs on CPU or GPU. But anyone that's ever done any programming at all knows that you end up having to do some pre-processing along the way. There are some things where you say, OK, I'm going to have to compile the code slightly differently on this system compared to that system. And you have pre-processing. One of the reasons you might do is that as well as the directives, OpenACC has some runtime library functions that you can call. And if you have those, you don't want those to be the compiler to see those if it doesn't support OpenACC. And there are occasions where you may need to change a loop structure for OpenACC. There's less than you think, because quite often you change it for the GPU, and it runs better on the CPU, because modern CPUs have much more vectorization capabilities. So quite often, a lot of the refinements that you make to your OpenACC code is a good way to speed up your CPU code. And similarly, when you do an OpenACC port, it's a great code audit. You go through your code line by line, and you clean up loads of stuff. So the CPU performance can go up in that sense, because you just clean up the code. But you can do conditional compilation. There's a CPP macro that's automatically defined, #ifdef underscore OpenACC, and it's set to a value if you really want to check which version of OpenACC is supported. So a first example. You wouldn't really do this on the GPU, but let's imagine you wanted to. You wanted to add two arrays together and put them into a third array. So what you would say is ACC parallel loop, your loop nest, end parallel loop. If it was C, you'd say #pragma ACC parallel loop, open brackets, 4, and then close your curly bracket at the bottom. And that's it. And then you compile it. The compiler does the work. It looks at these arrays that says, oh, you've got 3 arrays here, A and B and C, so I'll need to allocate some space on the GPU. C is a write-only array. So I don't need to move any data from the CPU to the GPU at the start. I just need to make some space on the GPU to hold the data. But I do need to do a data copy and move the elements of arrays A and B to the GPU. Then it's got lots of parallel tasks here within the loop nest. It has to split these up. It has to partition these loops, to work share these loops, so that these iterations are going to be spread across the GPU. So it writes a kernel to do this, and then launches this kernel, and it waits for the kernel to complete. And then at the end, it says, well, A and B, I'm going to free the memory in the GPU memory for A, B, and C. Actually, A and B were read-only. I don't need to bring them back. So I'll just throw them away. But I need to copy array C back to the host. So the compiler should, and in all honesty with the Cray compiler, I've never hit a situation where it's not got data movements correct. On occasion, and we will see examples, it can be overcautious. If you've got an iteration loop, it may say, well, this array C, on the second iteration, did I need any of the values from the first iteration? And sometimes it's overcautious, and it ends up copying the array C to the GPU at the start. It doesn't make the code incorrect, it's just inefficient. It doesn't do this with all of them, but there are occasions. And so then you can step in and you can help it. But the point is it gets most of it. It gets it correct, but it gets most of it optimally correct at the first thing. It'll spread these loop iterations over the GPU. If you've done OpenMP, only the outer loop gets split by default. With OpenACC, it will split more loops in the loop nest, 2 or 3. And it will split these across the GPU, and it will choose a way of doing this. It will choose a loop schedule. This may not be the perfect one. You can tune it yourself if you want to. But it's usually not bad. So this loop nest that's going to execute on the GPU, we call a kernel, similar language to CUDA. The loop iterations are divided up and executed in parallel. So you need a loop nest where the loop iterations can be done in parallel. There are 2 directives that we can use to create a kernel. One is called parallel loop, and one is called kernels loop. Both generate an accelerator kernel from a loop nest. You could use either. There are slight differences between them, and I'll come to what those differences are. We're going to use parallel loop for, well, I'll mention that later, why. So what about a whole program? Here's a very complicated program where we're going to populate the elements of an array, and then we're going to double the values of each element. So what do? Well, we say parallel loop, and that's it, and compile it. So the compiler will create 2 kernels here. The first kernel will initialize the array, and it will determine that this A is a write-only array, so it will only copy it at the end back to the CPU. The second one is a read-write operation, so it will copy array A to the GPU, it will double the values, and then it will copy the array back to the CPU. I've broken the parallel region here because I need a barrier. I need to make sure that this has finished before I do this operation. Because in principle, the way it divides up these loop iterations could be different for the two kernels. So I must make sure it's finished the first task before the second. There's no way to put a barrier inside a parallel region for the GPU because of the way the GPU works. The way you make a barrier is you end the parallel loop and then you start a new one. If you're doing OpenMP, you would say, I don't like the sound of that, that's going to be expensive. But that's another difference with OpenMP. In OpenMP, no, this is where you come in. But there is a mechanism. This is what I'll come to on the next slide. So there's launching a GPU kernel, however many microseconds you think it might take, is a cheap operation. Creating GPU threads is a cheap operation. You shouldn't worry about breaking a parallel region like this to give you a barrier. And the code, of course, can still be compiled for the CPU. Well, actually, it's a couple of slides on, but I'll come to this. If you've done OpenMP, you'll be familiar with the concept of data scoping. Data scoping means when we do everything in parallel, we want to get the right answer. And that means that all of the arrays and scalars, all of the variables in your loop nest, in your parallel regions, you want to make sure that they are treated in the right way. So variables in a loop nest are either shared or they're private. If it's shared, what it means is that all the loop iterations will process the same version of that array, same version of that variable. That could be a scalar. More typically, it's an array. There's an array. I want to process all the elements of this array. Each thread is going to do a bit of this work, but they're all operating on the same array. So that's a shared variable. Now, I mean, if you've done OpenMP, this is all very old hat. If you've not, that's why I'm kind of mentioning it. So in this example here, where I've got a loop nest, these arrays, A and B, are shared. Private variables are where each loop iteration has its own version of it, and it treats it separately. So here, this scalar T is a private scalar, because each loop iteration is going to do something separate with it. And what you understand is that each loop iteration has its own its own variable T to do its different things with. Loop variables are also private, because each loop iteration has its own version of the loop counter. First private, well, that's slightly different. It means that when I come into the loop nest, let's say T had been set to T equals 0 up here. When we get in here, everybody has their own copy of T, but they all start with the same value. And that's called first private. Loop limits should be first private. They could be shared, but so that's what happens in OpenMP. You've got this concept of shared and private. And there are clauses that say exactly that. Loop index variables private by default, but scalars are shared by default in OpenMP. So this is beware if you've used OpenMP. In OpenACC, private and variables are the same. The difference is that scalar variables are private by default in OpenACC. Shared variables are more complicated. And the reason they're more complicated is because as well as it being shared across all the threads of the GPU, you also have to say, and how is the data going to move? Is this data, do you copy it from the CPU and then share this array at the start of the kernel? Do you copy it back at the end as well? Or is it just temporary space? So a shared variable, a shared array that is used as a read-only in the kernel is copy in. A shared variable that's write-only is copy out. A shared variable that's used in a read-write manner is copy. And if it's a temporary array that's only used as a scratch workspace within a kernel, then it's a shared variable, but there should be no data movements, and create is the name of that.
Somehow from the perspective of the GPU, right? So I read only from the CPU. Read copy in means I copy from the CPU to my.
Yes, at the start of a kernel, and at the end, you simply free the GPU memory. So copy in plus copy out is the same as copy, because copy moves it at the beginning and the end. So it's like a superset of these two. So if we go back to this original version, the compiler was doing the scoping automatically. But if we decided, let's do it by hand to be sure, to be clear, the clauses that we would put in is copy out A here, because it's write only, so we just want to allocate space here and no data movement. And at the end, we want to move the data back to the CPU. And because this is read-write here, we want to say copy. We could do that because we would make data movements explicit, either because we want to or because the compiler is being overcautious. Now, as you pointed out, and I mean, the first thing you notice with this is this is a really stupid thing to do on the GPU, but if you were to do it, there's no need to copy this array A back to the CPU here, simply to send it back to the GPU for the next kernel. You know, it's like, you know, if you've got water, you know, it's sloshing from side to side. It's sloshing from the CPU to the GPU, backwards and forwards. And that you'll just waste all your performance doing that. So we need a mechanism to kind of keep data on the GPU and reuse it. And this is called a data region. And so this is where you've got an array like we had there, and we're using multiple kernels to process that data. We'd like to keep them on the GPU and only move the arrays when we need to. And so this is at the start and the end of this idea of a data region. So the way you do this is you say ACC data, end data, and there's a problem already. That should say hash pragma. Let's just change that now. And if you have a data region, the arrays or scalars that you specify will only move at the start or end of the data region and not on the kernels in between. So in our example here, what we would say is that create a data region that starts here and ends here, and it's spanning two kernels. From the point of view of this wider data region, array A is only used, it's initialized on the GPU, and then it's processed on the GPU, and at the end, we need to bring the values back. It's used in a write-only mode on the GPU, so we declare it to be copy out. So it's a shared array that's only copied back at the end. At the beginning, all we do is allocate space on the GPU. So the clauses that we use here, the shared clauses, are the same as before. There's no automatic, on the kernels, the parallel loop, if you didn't say, the compiler would work it out for you. On the data regions, you have to do everything by hand. You have to specify exactly which arrays will move and how they will move. Any array that you don't mention here, well, it does it automatically on the kernels as before, but if you have mentioned it, it doesn't do that in these kernels. It only does what you said it should do. The data region here is going around two GPU kernels, two parallel loop regions. The data region is a sort of, it can contain host code as well. So you could have some serial code in there that was doing something else. But what you need to remember is that serial code is running on the CPU. Within this data region, there are two copies of array A, one on the CPU, one on the GPU, and they are completely unsynchronized. Now, you say, well, you know, if I'm only working on the GPU, I'm wasting CPU memory, and that's true. And there are ways to avoid that, but they're more complicated. But on the other hand, the CPU has 32 gigabytes of memory, and you're typically running one process per node to use the GPU. And the GPU has 6 gigabytes. So there's much more memory on the CPU. So with at least the current generation, we don't need to worry that there's a copy of A sitting on the CPU that we're not using. If you want to really want to make your head hurt, You could use the copy of the array on the CPU for something different. But it'll work, but I wouldn't recommend it. Yes, yes, you'd start to change the portability if you did that. So you want to be very careful if you think that's a good idea. My recommendation would be not to do that. Have serial code inside your data regions, but don't use it on the copies of these arrays. Now, there's no automatic synchronization within this data region. The only synchronization occurs at the start and at the end. If you do need synchronization in the middle, there is a way to do it, and we'll talk about that a bit later. So that's, this is a very simple example. It's not a real code. But, let's do it to death. Let's just do everything from it. Let's make it look a little bit more like a real code. In a real code, you have a main program, but you have subroutines, and you call a subroutine. So here, I'm going to double the values of an array by calling a subroutine. So this is a call on the host. This is host code inside the data region. The data region looks the same. Inside here, I'm going to double the values of the array, but the way I'm going to do it is by calling a function. Now, you'd never do this if you were doubling the values of an array, but it's looking more like a real code, which has a call tree, and data is passed through the call tree. So how would we do this? Well, what we do is we say, okay, here it's fine. Because it's in the same routine as the data region, this kernel knows that A is on the GPU, so I don't need to do anything. I just put parallel loop there, and it will know to use the version of A from the data region. But when I call a subroutine, inside the subroutine, I'm going to say parallel loop for this loop nest, but I need to tell it, because it's in a different routine, and it's probably in a different source file, I need to tell it, use the copy. Don't try and do data scope movement yourself here. You should use the version of the array that's already on the GPU. So the present clause means use the version that's already on the GPU. And I say present B because when I passed the array through, I renamed it as B. So I say present there, and then there'll be no data movements with array B for this kernel, because it's within this. It's semantically within this data region, even though it's not actually sitting in the same source file. And then within there, I've got this function call. In OpenACC version 1, this will probably actually be implemented by the compiler inlining this function. In OpenACC 2, there's more scope for nested parallelism, but these are kind of details. But the idea here is that you've got the parallel loop and you've got these data regions. Data regions are what you put in to kind of start minimizing the data movement. Writing parallel loop over all your loop nests is quite an easy task. But what's hard is the fact that you have to go in and put the data regions in, and there are not the same degree of tools to help you with doing that. And that's because it's just very complicated, and you, as an application developer or application user, or as a scientist, you know how your application works. You know how data moves in your application through the call tree. So it's you that has to put the expertise in. This is the hard thinking that I'm talking about. It's not writing your data clauses, it's knowing where to put them. If you've done OpenMP, you'll have heard of reduction variables. It's where you want to combine values across loop iterations because you're summing the values of an array. So you want to combine all the values of the array into one value. Or you want to take the maximum of an array or the minimum or do some sort of logical operation where you're reducing all of the values of your array down to one number. And you need to tell the compiler to do this properly. And to do this, you have to tell it that this, so in this example here, T is summing up some values from an array, and U is taking the maximum of some values from an array. So if I want to put this onto the GPU and parallelize it, I need to make sure that it treats T not just as a private scalar, but also as a reduction variable. So what I need to do is I need to say ACC parallel loop, but I also need to say reduction, and it's a sum, and the variable it's being reduced into is T. And so I would have to put this clause, this extra bit, onto my parallel loop directive that would sit up there. And I would also need to say, put a reduction clause for u. U is taking a maximum, so I tell it it's a maximum, and it's on u. I have to tell it what the operation is because that's to do with initial and final values and how they're combined. So you need to tell it what sort of operation it is. OpenACC only allows reductions to be done on scalars, not of array elements. So if you're summing up one big array and putting it into values of a smaller array, you won't be able to do that straight away with OpenACC because the compiler finds it very difficult not to just completely fill the GPU memory with private copies of arrays. You can only do reductions on scalars. So what you would probably want to do is use a temporary scalar rather than reduce, and then put that temporary scalar into the reduced array. So what have we seen today so far? You get compute regions, loop nests, and you use the parallel loop or the kernels loop directives to create them. Minimizing data movements is really important, and the data directive does that for you. But especially with data regions, you need to control how data moves. And so you use these data clauses for that. In OpenACC 2, there's a default none. If you really want the compiler to do nothing, and you do everything by hand explicitly, because that's the way you like to work, you can say default none, and then you go in and you have to specify everything. In OpenACC 1, they didn't have this, and people said it would be very useful. So this is in there now. So it's up to you. You can either use this and do everything by hand, or you can use the automatic scoping and then check it and correct what you need to check. It's up to you. But there's no automatic scoping in data regions. You have to do it. The shared clauses, copy in, copy out, and create. And the private clauses. And then there's this present clause, which is where you say the data's already on the GPU, you should reuse that copy. And when you do real applications, you use the present clause far more than you use these. You tend to use these right at the start of the code. You have a big data region that essentially starts in your main program and covers the whole call tree. And then within the call tree, you're using the present clause all the time. And that's how a typical science engineering application gets ported. So we've gone a little bit over here, but these are the basics, so we should go slowly. You now need to know everything. You now know you need, easy for me to say. You now know everything you need to do to accelerate a simple code. And the simple code we're going to do is a scalar Himeno benchmark. It's going to port the whole code to the GPU, but crucially, it's actually going to do this, and it's going to be faster than the whole CPU. We haven't done any tuning. The only tuning we've done is understanding data movements. So, we've done maybe not even page 1 of this. We've done a tiny amount of this book, but in doing so, we've got to the point where we can actually get a code that's running faster on the GPU than the CPU. I think we end up putting in 7 directives in a 200-line code. All of the rest, the tuning, is important, and it does come in, but the point I kind of want to get across here is that you don't need all of that to get going. And you can do a little, you don't just do toy examples but get no performance by doing it this way. So are there any questions, any more questions on these basic ideas? Yes?
When I'm in a data region, do I need to specify everything? Or can I just specify one area? He's using the default scoping for the other ones.
Yes, exactly. You can specify typically for big, if you've got a code with big arrays, you would probably in the end be specifying all of the big arrays. But you can do it one at a time. And ones that are not specified will be automatically moved. And obviously that will hit performance. But when you're porting your code, you want to do it step by step, and you want to keep checking for correctness, not worrying about performance as you go. So it can be very useful to do it one at a time. So you say, I will have no data region, and everything's moved automatically. And then I put a data region in, but only one array. I'll get that array, and I'll understand and make sure that it's being used correctly. And then I'll do another and another, and the performance will increase as you move more of them to be explicit in the data region.
Not
Yep.
kind of relating to that. Your very first example is adding two arrays.
Yes.
That work right away like that, and I was very surprised. You cannot create races or something.
There's no race conditions there. I mean, OpenACC, because of the execution model, because of the memory model, you can have race conditions. You can, it won't stop you getting them. The compiler does help in some places, but for that operation, there's no, I mean, that's so data parallel, there's no race condition there. Because every loop iteration is completely independent of the other. So there's no possibility really to get a race condition on that. You can get race conditions in other things, but usually, I mean, the compiler is very good. Usually the race conditions come when you try to sort of optimize and you override what the compiler was trying to do. Generally, you don't get race conditions out of the box, straight away. They come in as you optimize. But correctness checking is really important all the time, every step. Yep. Yes, the support for structs and objects like that was in OpenACC 1 was not very good. So a lot of the work that's been done in OpenACC 2 is to improve the support for things like structs. If they're just basic structs, that's fine. If they're structs that contain pointers and things like that, that's really a problem because it's when you say move this data to the GPU, it's a deep copying problem to know exactly what the real numbers are as opposed to, and then it has to reconstruct all of the pointers on the GPU. You can do this, but you may have to do it by hand at the moment. Yes? You have single and double precision the same way. Whether you will get, you're unlikely to get a bitwise reproducible number on the GPU compared to the CPU. The architecture is different. The underlying runtime libraries do things in different ways, especially for things like reductions. The order in which the reductions are done will be different. So, especially because the thread blocks, you don't quite know how they synchronize and what order the reduction ends up being done in. It makes it, in order to enforce a bit reproducible, even on the GPU, a bit reproducible reduction would be very damaging for performance. I mean, I think if you really were concerned about that, you would probably, you'd be using the runtime API quite strongly. I think you'd probably almost be better using CUDA. But one of the things that I haven't talked about and I will talk about later is that CUDA and OpenACC are interoperable. So you can process the same data on the GPU using OpenACC and with CUDA. So in your application, what's a good way to go about it? Port it with OpenACC. If you decide that you need CUDA for some low-level control or because you have a very optimized algorithm in CUDA, you can use that for particular computational kernels, but you don't have to write CUDA for the entire application. But if you're really worried about that, and I know, if you're doing weather or climate or things like this is a big concern. This is a general problem with GPUs, I think. It's a different architecture to the CPU. So you can't expect to get 16 digits identical. Yes? In some cases, it will work, but in general, I would say no. If John Levesque were here, who's one of the Cray people from Oak Ridge, I mean, he's been doing Fortran for a long time. He hates array syntax. He hates it on the CPU. He says it's disastrous. It's disastrous for cache usage. You should never, ever do it. But it's kind of neat. But I think for OpenACC, you are better expanding the loops, partly because it supports it, but also when if you do come to performance tuning, you generally want the loops exposed. I mean, with the Cray compiler, it's kind of supporting array syntax for OpenACC. Of course, it could be done. But actually, it's much more difficult than you would think, and it's because, this is where knowing the compiler developers helps. Where everything is done in the optimizer, it doesn't just expand everything into loops as the first step and then follow everything else. The loop expansion comes much lower down, and the OpenACC and all the directive processing has gone on higher up. So it is actually far more problematic than you would think. Sometimes it works, but I wouldn't recommend it. Yep. There isn't. There are facilities that I will talk about where you can make a runtime decision on these sorts of things. The reason that this tends to not be, it's the kind of thing you think is useful, but then when you start working with applications, you realize that because data locality, because data movement is so expensive, you kind of want your data to be staying on the GPU as long as possible. And then you want to process it on the GPU, even if this kernel takes no time or is inefficient, compared to moving the data back to the CPU and then back to the GPU again. It's better to just keep everything on the GPU. So there are facilities to do that, and if you have something where you have the data living mainly on the CPU and then you offload some things. I mean, if you use the Cray, there's a scientific library that provides dgems and so on, and there's an accelerated version of that. And if you're running a code on the CPU, it will look at this dgem operation and it will make a decision, and it can pattern match it away and say, actually, it's cheaper to move that to the GPU, do the dgem there and bring it back because the problem size is large enough. And you can do all of those within your code, but there's no automatic mechanism for that. Yes, I'm not really going to do examples of it, but I'll mention what the things are that you can use to do that. Yes?
A short question. At one point you said linked lists are not so well supported, links to arrays or links, pointers as arrays, or I'm not sure. Can I use as simple as that array like a dynamic allocated?
Yes, you can do that. In the practical example, if you look in, we're not going to, the practicals, which we are slightly behind on, but these are good questions, so I'm not worried about that. There's 4 practicals in there. There's practical 0, practical 1, practical 2, and practical 3. Practical 1 we're not really going to talk about, but what it is there for, it gives you examples of doubling the array, but it does it in Fortran or C, and it does it with either dynamic memory allocation or static memory allocation, and shows you what you do. So you can deal with all of that. That's fine. Dynamic. It's just if you have very complicated data structures, graph data structures, these sorts of things, you may end up having to use the runtime API to reconstruct all these pointer nests on the GPU yourself. It can be done. It's just not quite so pretty, and it's hard. It's getting performance once you've done that. We could talk about it. I mean, we could talk about it tomorrow morning or during the breaks today if you've got an example you want to look at. So although we are slightly behind, practical 0, the idea of practical 0 was just to make sure that your accounts worked and you could run jobs. How many of you have used the CSCS systems? Some of you. The idea of these practicals is that you've come here to learn OpenACC and you've not come to learn how to use Cray systems. If you want to learn how to use Cray systems, there's courses you can come to learn how to use Cray systems. So the practicals have been very automated. There are make files and there are build scripts and the build and submit scripts. And the submit scripts will write a job script for you and run it and tell you where the answer will be. Now you may say, I prefer to do everything myself. Well, if you run those commands, it'll tell you what commands it's executing. You're free to do those yourself. But I've tried to automate it a bit more to make it easier to get through the practicals in the time that we have and insulate you a little bit from the details of the system that you may not want to learn right now. Still, it's useful to understand a little bit about the system. There are when you log in, there are no GPUs where you log in. You don't run your code there. You have to run your code on separate nodes where there are GPUs. So you have to do it through a batch script. And there's a Slurm jobs control system, and you write a script and you submit it to that, and it then executes it and the result is returned. So that's why there's a submit script in all of these examples. It writes this little job script for you with the special header and submits it with all the special options. And you can look at this to see what it is, but it's fairly automated to do that. You've got a home directory, which is where you can compile your code and whatever, but jobs should be submitted from the fast parallel file system. It's a Lustre file system. You find this /scratch/turdy/ whatever your username is. Again, the submit script will make a directory there and run it from there for you. And it will print what that directory is and tell you where to find the results. The login nodes that you log into, it's Linux-based. You're in a bash shell. You've got all the usual Linux commands. Software is controlled using the GNU module command. You shouldn't need to do very much with that. You can change which compiler you use by changing the programming environment module. When you log in, you get the Cray one, and that's the one we're going to use for this. If you want to use a different compiler, then you change that module. One thing you must always be sure of is always make sure the Cray PE Accel Nvidia 35 module is loaded when you want to do GPU stuff. If it's not loaded, you'll be able to compile, you'll be able to run, but you'll think it doesn't go very quickly because it's running on the CPU, because it's not recognizing the OpenACC. I think by default on Turdy it is loaded. Or is it? No. Because some people might want to run on the CPU and they don't want this module loaded. Every time you log in, you have to reload it, and it's easy to forget. When you use the compilers, you use commands ftn cc. These are wrapper scripts for the real compilers, which are called Cray ftn and Cray cc. And there are man pages for those to find out about compiler options. To make sure that you're running with the right CPU options, you have to make sure that a module is loaded to tell it what CPU you're using. I know that you're running on the GPU, but even so, you don't want any illegal instructions or anything. I think these are loaded by default. You should see Cray PE Interlagos on Turdy. You should see Cray PE Sandy Bridge if you were on Daint or the Swan system. Cray compiler, OpenMP is supported by default. If you don't want it, switch it off with the compiler flag. Code is optimized by default. The Cray compiler doesn't tell you very much when it's compiling. If you want to find out how it compiled the code, you should switch on messages, the compiler listing file. So you should use the compiler flag hlist equals A for all. When you submit a job, you have this job script, and within there you'll see a command ap run. That's like MPI run if you've used a cluster. This is the job that actually runs the code in parallel on these nodes. To see which jobs are running, you use the sq command. If you want to just see your jobs, you can use your username to see which ones it is. If you decide you don't want to run the job anymore, you can cancel it. Yep.
One comment, when you log in to ELA, then it automatically creates Scratch for you.
All right, brilliant. Okay, so there's an environment variable. These are the details of the Slurm script. I'm not going to talk about those because it writes the script for you. A typical job script would look like this. The name of your job, one node, one task per node, and that's where the output's going to be written, and this is the maximum time the job will run for. And then down in here, if you want to use OpenMP, you have to set the number of threads, and here it runs a code there. So, before we have coffee, you should do practical zero. Practical zero takes no time. It's basically to check that the accounts work. But what it also does is it runs two commands. One's called Nvidia SMI, one's called PG Accelinfo. These are useful commands to kind of just have in your back pocket because they give you information about the GPU. They tell you what GPU you have, whether there is a GPU. If you think the GPU is faulty on the node, you can test it with these. It'll tell you about what bandwidth you can get for data transfers, how many SMs there are, basic information about it. It's a good thing to have if you just get on a system and you want to just know something about the GPU, what driver version is it using, this sort of thing. All of this information you can get by running these commands, so practical zero, you'll just run those commands and get the output. So there should be a tar file in my home directory. Can anybody see it? Have I got the permissions right?
Yeah.
Are the permissions wrong?
No, they're right. Yeah.
Oh, is it not so? Oh, right, sorry.
It should type everything it should do.
Okay. So it's called Cray underscore OpenACC underscore training.tgz. So if you copy that file out into your home directory, or wherever you want to put it, and then unpack it. Oh. That's what comes of writing these slides to last minute. If you go into the top level directory, there's a license file, which you of course should read. And there's a README file, which you definitely really should read because it actually has information on the practical. But to run the practical zero, what you do is that I've written a little setup script, and that setup script will make sure that the right modules are loaded, including the Cray PE Accel Nvidia 35 module. So before you do any of the practicals, you should source. Don't execute, don't type bash that script. You should source, type source tools Cray setup.bash. And that should set up the modules for you. If you then go into practical zero, well, there's no executable because it's just running system commands. You should just be able to type bash submit.bash and your job should run. Has anybody got that far? Sorry, that's the first question. Has everyone managed to log in? I mean, you could do all of it. If you have an account on Turdy already, you could use that. It's just it's unlikely you'll be able to use the... Have you... No, it's bash submit. That's a bash script that will do the sbatch for you. It'll write the script. The reason I did this is because if you actually look in the tools directory, there are header files for Slurm, for PBS, for Moab Talk, and that's because we have so many different systems. No, I just got tired. Every time I went to a different site, I'd have to rewrite these and get it wrong. Yeah? Is it running? Did I get the reservation name right? Yeah, when you run that script, it will say running in /scratch /turdy, whatever.
Invalid account.
Ah, right.
I mean,
Have I got, if you look at the resubmit.bash script, does that give you the right?
Yeah.
If you cat
if you do resubmit, it will dump the file. You need to do a list. I don't know. The first time for me was empty.
To port a code, you don't need to know much of OpenACC. OpenACC, I mean, they have what they call a quick reference guide, which doesn't seem so very quick these days. But there's a lot in there, and it gives you a lot of flexibility and a lot of things to do, but a lot of this is more advanced. To actually get a code up and running, you don't need to know very much. So what I will talk about in this first lecture will be enough to port this simple code. You won't get the optimal performance, you can tune it, but the point is you can port this code to run entirely on the GPU just using that knowledge. And you'll get a chance to do this as well before lunch. But then in the other lectures, I'm going to talk about the more complicated things and the ways that you can get performance and the ways that you can deal with real codes that contain sort of real computational tasks as opposed to the simple examples. So I don't want this to be something where you just go away and you've got hello world and that seemed to run fine, but then you go and you take a real code and you say, well, where do I start? You know, what do I do? That's not what this course is about. This course is, I'm assuming that most of you here work with real applications, industrial, scientific, engineering, whatever, but they're doing real tasks, and you're going to want to port the entire application, and you're not just interested in a very simple example. So, how many of you here have used GPUs before? Right. I'm not really going to assume you have. If you've used CUDA, some of the language will be familiar. If you've not used CUDA, you don't need to know it in order to do this. Similarly, how many of you have done any OpenMP programming? So a similar proportion, about a half. Again, OpenMP is a similar programming model that you use on the CPU. If you've done OpenMP, there are some similarities with OpenACC. And there are places where I'll sort of say, this is the same as OpenMP, or this is different to OpenMP. But you don't, again, I'm not relying on you knowing OpenMP in order to do this. And similarly, all of the practicals that I'm going to talk about, except the only thing is when I say porting a parallel code here, this is some extra things if you have a code that's got MPI in it. This may be relevant to you, it may not, but that's the only place where I'm really going to be talking about a message passing parallel code. So before we start the main course, so I kind of talked mostly about this. My background before I joined Cray was I worked in lattice QCD, calculations, theoretical physics. So I always think that I come to computers with more of a user view than somebody who's kind of come from compiler science, you know, a computer science compiler development type of point of view. So in some cases, I'm probably going to skip over details, either because I don't think they're that relevant, or more likely because I don't understand them. So please ask if things seem a little bit high level. But the other reason for that is that unless you are trying to get the last few % of performance out, you don't really want to care about the architecture. I'm guessing most of you have run a code on a CPU. How many of you do any assembly language programming? There's always one. But most of you don't. But you could get better performance on the CPU if you rewrote your application in assembly language. But you don't, because you want a portable code. And that's the same approach I'm taking here, is that, yes, if you really get down and you write your kernels in PTX, you'll probably squeeze a bit more performance out of the GPU, but it won't be very portable, and in some ways it won't be very productive in that you'll spend a lot of time to get that extra performance. If you want to do that at the end, well, that's the sort of the last stage of optimization, but that's not where you want to start from. So again, that's the approach I want to take with this. But it does help to have a little bit of an overview of the architecture that you're using, because some of the language that I use kind of relies on what's happening underneath slightly. and also allow you to make incremental changes to this code so that it can be run on a hybrid multi-core system, an accelerator, which at this stage, I mean, we're talking specifically about the Nvidia GPUs that are sitting in this machine, but it's more general than that, and it can be applied to other architectures. And you do this by recompilation and some tuning as opposed to a complete rewrite. So OpenACC was launched at Supercomputing 2011, so that's 2 years ago. It got an award last year as a technology to watch. This year it got 3 awards from HPC Wire, 1 Reader's Choice Award and 2 Editor's Choice Awards. So these were displayed on the booth at the Supercomputing conference, and Cray was there giving a tutorial very similar to this. So they have these tutorials on the Sunday and the Monday, and we had an all-day tutorial on the Sunday to teach people about OpenACC. And of course, you come back fired with enthusiasm. I must change this, I must update this, this didn't work very well. So I've made a lot of changes, so I apologize if there's places in the slides where something's slightly out of date. I will correct that before I distribute the PDFs, which I think you can put them up on the website, can you? The PDFs for the talks. So please bear with me if there are any mistakes. So one of the things that I decided that I would change was to split the material up a little bit more through the day to make it into, so rather than having 1 or 2 or maybe 3 lectures on OpenACC, I've split it up into six sort of parts of the programming model as we go through the day, and they kind of build in complexity. So we also have some, well, hopefully a live demo. This is a bit of an experiment. If not, we will, I have a worked example where I go through taking a simple code and putting in OpenACC and running it and showing how the performance changes as you go through the porting process. It's a very simple code. I mean, it has to be if you're doing it in a demo there. And you'll notice that it's very early on in the day. It's just after the coffee break. And the reason for that is that so as Themis has explained, every time I come to visit CSCS, this is my 3rd visit now, so it's a pleasure to come back and see new users and help people to use these systems. But everything just gets bigger. When I came here before, the first time, it was the old site away over the hills. There were donkeys outside, and there were just 2 cabinets of Cray XK6 with Fermi GPUs. When I came back, I think it was February time this year, there were 3 cabinets of XK7 with the Kepler GPUs. And suddenly you come back and there's 28 cabinets of GPUs. So if I do get the opportunity to come again, I hate to think how many cabinets I may find if this increase continues. It is, I mean, Cray is very proud of this machine. It's certainly the very biggest hybrid machine that we have installed. It's on the Green 500 list, as was pointed out, it's orders of magnitude larger in size than the machines above it. And it's the biggest supercomputer in Europe. We're very pleased with that. But using a hybrid multi-core system like this is not easy. It's not as straightforward as before. I mean, you can say whatever you like. There's all sorts of tools to make it easier, but it is more difficult. It does require some user effort to get your codes up and running on these systems. So what I'm going to talk about today is OpenACC, and this is an endeavor, a sort of cross-vendor recognition across the industry that these things are difficult to arrange. It's difficult to get your codes across to there. So we must provide a programming environment that makes it easier. I mean, if you want to say what is a programming environment, it's something that kind of it bridges the gap between the peak performance of this machine and what you can achieve with your code as a real user doing a real calculation. So OpenACC, or OpenACC as I will sometimes call it, is an effort to make this, to take a code that you have that's running on the CPU, and you cannot ignore the architecture because a GPU is a very slow serial machine. It's a very good machine when you use it properly, but you have to understand a little bit about the architecture to get the good performance. So the Cray XC30, and also, I mean, the XK7, like Turdy, are very similar. They have nodes linked together with an interconnect. For the XC30, it's the Cray Aries interconnect, which is a sort of multi-level all-to-all network. It uses 3 levels of all-to-all, 2 with copper wiring, and then it also uses optical cables between groups of cabinets. So it gives you very good global bandwidth. And this amount, actually, the amount of global bandwidth is tunable. You can choose how many optical cables you put into your system. And one of the amazing things about the machine at CSCS is that it's one of the first systems, well, that we could talk about, that has the full complement of optical cables. So this machine has the best bandwidth of any Cray XC30 that you would ever be able to use in the world. So another great feature of it. On the node, you have one CPU, which on PISDount is an Intel Sandy Bridge, 8 physical cores, and it's got one Nvidia GPU, a Kepler K20X. Turdy has an AMD Interlagos CPU, but the same GPU. And it has the previous generation of interconnect, the Cray Gemini. For this course, that's not going to affect you because we're not really using the interconnect. And as we've talked before, power is a big thing. Why are we interested in accelerators other than we're using them now? If we're going towards exascale machines are going to have a lot more computational power, but without using physical electrical power to run them. The DOE says it'll fund an exaflop machine, but it only wants it to be 20 megawatts. Well, the Jaguar system at Oak Ridge, to get a petaflop, was using 6 megawatts. Things have improved since then, but not to the point where we can get 1,000 times more performance with 3 times the power budget. So accelerators are going to be very important.